Hello students, welcome back. We are still in section 1 of this notebook. Apparently it is taking longer than I thought it would. Nonetheless, I don't want to miss the review because we are talking about some tricky and important concepts here. Let's review the concept of kernel and image yet again. Kernel is a set of all original vectors that are being sent to the zero vector. Image is a set of all image vectors that actually came from the original. So the arbitrary elements from image look like this, some f of v. And then we prove that kernel and image are subspaces. We went through some examples, and then we went through a couple of important theorems on images. If the original vectors v1 through vn generate v, the original vector space, then the image vectors f of v1 through f of vn generate image of f, the image space. 1.5 is backward. If the image vectors f of v1 through f of vr is linearly dependent, then the original vectors v1 through vr is linearly dependent as well. So we are talking about two complementary concepts, generators and linearly dependent, and forward direction and backward direction. Eventually, we are going to talk about the linear independence on forward direction in 1.7, but we need some preparation here. A linear map is one-to-one if and only if the kernel is zero. So kernel has just zero vector. That means f is one-to-one map. In other words, the inverse exists and things like that. Okay, let's remember that and let's go over to theorem 1.7. Let v and w be vector spaces and let f from v to w be a linear map such that the kernel is just zero. That means f is a one-to-one map. All right. Suppose further that v1 through vn is linearly independent, then f of v1 through f of vn is linearly independent as well. You see, here in 1.5, if the image vectors are linearly independent, then the original vectors are linearly independent. We established that, but not the other way around. If the original vectors are linearly independent, then will the image vectors also linearly dependent? That's not certain. We didn't do it there. Also, for generating, we did. The original vectors are generators, then the image vectors are generators. That one we did. The linear independence, we didn't do it for the forward direction. In general, we can't. And that's why this condition is necessary. We need f to be one-to-one. Okay, the first statement is the forward direction of 1.5. Okay, yeah, 1.5. You see, backwards direction, images are linearly independent, then originals are linearly dependent. That's once established. The forward direction, we'll have to do that under the assumption that f is one-to-one. So the first statement, that's something we have to work on. How about the second statement? As a matter of fact, that's much easier. If v1 through vn is a basis of v, then f of v1 through f of vn is a basis of image. Let's see. We already proved that if v1 through vn generate the original space v, then the image vectors f of v1 through f of vn generate the image space. We already proved it in 1.4. And then in the first statement, we just did v1 through vn is linearly dependent, then f of v1 through f of vn is also linearly dependent as well. So linearly dependent and generators, that means spaces. And the conclusion, linearly independent and generators, so that means spaces. So the second statement is nothing more than just a combination of the first claim and 1.4. First statement and so basically there's nothing to prove. As for the first statement, we need some work. So what do we have to do for the first statement? We have to prove that this is linearly independent, right? So this is linearly dependent. That is x1 f of v1 plus if that's zero vector, then all the coefficients must be zero as well. And that's what we have to prove. Now, what do we know? What do we know? We know these are linearly independent. Come on. Okay. All right. V1 through Vn is linearly independent. So if x1 v1 plus all the way up to xn vn add up to zero vector, then all coefficients are zero. That we know. We have to use this to prove that. Ready? Okay. We know that v1 through vn form a linearly independent set. So if we have linear combination that add up to zero vector, then all coefficients are zero. We know that. And this is what we want to prove. Linear combination of f of v1 through f of vn add up to zero vector, then does it mean all the coefficients equal to zero? That's what we want to prove. So let's work on that. Okay, this is equal to zero, and let's apply the property of the linear map. That is, it preserves the linear combination, so we can write like this. We can pass all this linear combination inside, and we can conclude like this. Does it make sense? The left-hand side and this left-hand side, they're the same, right? Okay, that's by the properties of the linear map, which preserves the linear combination. Now, f of this is equal to 0. That means it belongs to kernel. And I highlighted punchline a little bit prematurely. Okay, so we begin with what we are given here, what we want to prove, and then we use the property of the linear map so that we can pass on all these linear combination inside. Now, f of this vector is equal to the 0 vector. That means this vector belongs to the kernel. That's the definition of the kernel, wasn't it? Kernel is set of all vectors. F of something is equal to 0. F of this linear combination is equal to 0, so this linear combination belongs to the kernel. But then again, wait a minute, kernel has only one element. Kernel is just 0. So that means that equals to 0. And that's where I use that blue condition. Kernel has only one element, blue. Alright, what did you end up getting? x1 v1 plus all the way of 2, xn vn is equal to 0 vector. Wait a minute, we are right here. So what do we have? All the coefficients must be 0. And this one came from that red condition. And this completes the proof. Let's recap. We had 1.4. If we want to Vn generate the original vector space, then the image vectors f of v1 through f of vn generates the image space. Alright, but linear independence, that's a different story. We have backward. We have the image vectors, f of v1 through f of vr is linearly independent. Then the original vectors, v1 through vr, is linearly independent. Not the forward direction. However, we want to prove the forward direction here. v1 through vn form a linearly independent subset. Then the image vectors f of v1 through f of vn form a linearly independent subset as well. But then again, in general, it's not going to work, so we have special condition. F is 1 to 1. Kernel is 0. How to do that? Well, let's set up. This is what we want to prove. Let's set up linear combination, adding up to 0 vector. And whenever that happens, then we have to have only zeros. That's what we want to prove. We didn't prove it yet. It's just something what we want to prove. And then, what conditions can we use? Well, these are linearly independent, that's given. So if I have linear combination of v1 through vn adding up to 0 vector, then all the coefficients are 0. That one we know. And we'll have to use these to prove that. So we're going to prove this, so let's start from the left-hand side, okay? So set up the linear combination is equal to 0, and let's apply some algebraic manipulation. Let's pass on the linear combination inside, and that's equal to 0. And here is an important observation. This vector is going to the 0 vector. In other words, this vector belongs to the kernel. And that was the hard part. Now, from this point on, it's not too difficult. Kernel has only one element, 0. So if it belongs to the kernel, then that means it's a 0 vector. Okay, it's a 0 vector. And then if it is 0 vector, we are in the situation. So we can use this red statement there and conclude that all the coefficient must be equal to 0. And that's what we wanted to prove all along, wasn't it? So that completes the proof. So if v1 through vn form a linearly independent subset, then the image vector in the image vectors f of v1 through f of vn is also linearly independent, and that works only for the special case where kernel is just 0. And how about the second statement? If those are bases, then those are bases as well. Well, linear independence we just did. Generators, we did it before in 1.4. Put those together, then we get what we want.